All right, class. In this video, we continue our discussion of section 4.6 in your textbook on modeling with exponential functions. And we are working with Newton's law of cooling in this video at the top of page 5 of your lecture handout. In this example, we're given Newton's law of cooling is used in homicide investigations to determine the time of death. The normal body temperature is 98.6 degrees Fahrenheit. Immediately following death, the body begins to cool. It has been determined experimentally that the constant in Newton's law of cooling is approximately K equal to 0.1947, assuming that time is measured in hours. Suppose that the temperature of the surroundings, right, the air temperature, the surrounding air temperature is 70 degrees Fahrenheit. Find a function capital T of little t that models the temperature T, little t hours after death. Well, in this problem, T sub s, right, the temperature, the surrounding air temperature is 70 degrees, and the difference between the initial body temperature and the temperature of the surrounding air is 28.6. You got to think in terms that when the deceased died, the body was 98.6 degrees, and then the surrounding air temperature is 70, and so that difference is 28.6 degrees. So substituting for T sub s, D0, and K into the function for Newton's law of cooling, we have the temperature capital T at time little t is equal to 70 plus 28.6 times e to the minus 0.1947 little t power. So this is our model, right, for these homicide investigations, estimating the time of death. So in part B, you're asked if the temperature of the body is now 78 degrees Fahrenheit, how long ago was the time of death? So to determine that, to estimate the time of death, right, we've got to replace capital T of little t up here with 78 and then solve for little t time. The value of little t will tell us how long the deceased has been dead. So replace capital T of little t with 78, and now we're going to solve for little t. So first we subtract 70 from both sides and get 8 on the left hand side, and then to undo this multiplication, right, we divide both sides by 28.6 and we get 0.27972 on the left hand side is equal to the exponential e to the minus 0.1947 little t power. Now, in the previous example, we took the natural log of both sides in solving for little t. I'm going to take a different approach in this problem. This is an exponential equation, right? E is the base and minus 0.1947 t is the exponent, and 0.27972 is the value of the exponential. And so converting from exponential form to logarithmic form, we have the exponent minus 0.1947 little t is equal to log base e of 0.27972. Remember, the base of the exponential and the base of the logarithm are the same. Well, log base e has its own notation. It's ln. So remember, that's where the ln came from. It just replaces log base e. So when we replace log base e with ln, we have minus 0.1947 t is equal to the natural log of 0.27972. Now, we're solving for little t, so we got to divide both sides by minus 0.1947, and we have little t is equal to the natural log of 0.27972 divided by minus 0.1947. And so when you using your calculator, when you take the natural log of 0.27972 and divide by minus 0.1947, you get little t is equal to 6.5 hours rounded to the first decimal place. So the deceased, right, our estimate for how long the deceased has been dead is 6.5 hours.